In October of 2019, one of the most familiar stars in the night sky started doing something it had never done in the era of modern telescope-assisted astronomy. Betelgeuse, the bright reddish star marking the shoulder of the constellation Orion, began to fade. By early February of 2020, it had dropped to roughly a third of its normal brightness, the faintest astronomers had ever recorded it. The drop was so obvious that people who had never looked twice at a star chart before started noticing it with their own eyes. Headlines around the world ran with the same electrifying question: was Betelgeuse, one of the closest massive stars to Earth, finally about to explode? Amateur astronomers pointed backyard telescopes at Orion every clear night that winter. Astrophysicists fielded interview requests from major news outlets on a near-daily basis, and social media filled with only half-joking countdowns to the end of the world, even though nothing about a Betelgeuse supernova would actually threaten Earth at all. Professional observatories quietly redirected instrument time toward the star, just in case, and at least one research group began actively monitoring neutrino detectors on the off chance that the earliest possible warning signs of a genuine core collapse might already be arriving. Betelgeuse is a red supergiant, so enormous and so late in its life that astronomers have long known it is destined to end in a supernova, an explosion so bright it could briefly outshine every other star in the sky. For a few tense months, a huge number of professional and amateur astronomers genuinely wondered if they were about to witness that explosion happen in real time, an event that occurs in a galaxy like ours only once every few decades and has not happened close enough to see with the naked eye in over 400 years. Most supernovae detected by modern telescopes occur in galaxies millions of light years away, faint smudges of light captured only through long exposure photography, which is exactly what made the possibility of one happening close enough to see with nothing but the naked human eye feel so genuinely electrifying. What they eventually discovered instead turned out to be almost as strange as an actual supernova, and it forced scientists to rewrite what they thought they understood about how dying stars behave in the years before the end. To understand what really happened during that strange, fading winter, and what it tells us about the far more violent event still waiting in Betelgeuse's future, it helps to first understand exactly what kind of star we are dealing with, exactly how far away it actually is, and exactly how astronomers have come to know so much about a star none of us will ever be able to visit in person. Betelgeuse sits roughly 548 light-years from Earth, according to the most precise modeling done to date, a 2020 study led by astronomer Meredith Joyce that used pulsation data to recalculate the star's true distance, placing it about 25% closer than earlier estimates had suggested, a correction significant enough to meaningfully change how astronomers understood the star's overall size and mass as well. It is a red supergiant, one of the largest and brightest stars known, with a luminosity roughly 87,000 times greater than our Sun. Its radius stretches out to around 764 times the radius of the Sun, big enough that if you dropped Betelgeuse into the center of our own solar system in place of our star, its outer surface would swallow Mercury, Venus, Earth, and Mars completely and reach out to roughly 2/3 of the distance to Jupiter's orbit. Despite that almost incomprehensible size, its mass is comparatively modest for a star of its class, somewhere between 16.5 and 19 times the mass of our Sun today, having likely started its life at somewhere between 18 and 21 solar masses before shedding material over millions of years. If Betelgeuse were a bucket, you could fit roughly 300 million suns inside its volume, and yet weigh out only a tiny fraction of that many suns worth of actual mass. A reminder that, in the world of red supergiants, size and weight are almost completely disconnected from one another. The star's name itself carries an odd history of its own. It comes from an Arabic phrase originally meaning something close to the hand or shoulder of the giant, referring to Orion. But centuries of transliteration between Arabic and medieval Latin, along with at least one well-documented copying error, gradually reshaped the pronunciation into the form we use today, close enough to the English word Betelgeuse that the star has become something of a linguistic joke among casual skywatchers ever since. Astronomers have been watching Betelgeuse change for far longer than the events of 2019 might suggest, too. Its variability was first formally documented in 1836 by the astronomer John Herschel, son of the famous William Herschel, who noticed the star's brightness shifting over the course of months and published his observations at a time when the very idea of a star changing brightness on human timescales was still a genuine scientific novelty. To really appreciate the scale of the gap between us and Betelgeuse, it helps to imagine actually making the trip. Step aboard a hypothetical spacecraft capable of moving many times faster than light and start the engines. Within seconds, you have already covered 240,000 miles and you are passing the moon, a distance that would take a conventional rocket about 3 days to cross. Moments later, you are near Mars, a trip that normally takes real spacecraft around 7 months. where a small fleet of rovers and the Ingenuity helicopter have spent years exploring a planet with roughly a third of Earth's surface area and about a tenth of its mass. Push on, and you have to start dodging debris as you cross the asteroid belt. A scattered ring of rock and metal left over from the solar system's earliest days that never quite managed to coalesce into a full planet, home to the dwarf planet Ceres, whose surface area is only slightly larger than that of Argentina, and whose total mass is about 1% of our own moons, though the entire asteroid belt combined still adds up to roughly 25 times less material than the moon carries on its own. Despite science fiction's love of depicting the belt as a chaotic minefield of tumbling rocks, the objects inside it are actually spread across such a vast volume of space that real spacecraft can have flown through it multiple times without ever needing to dodge anything at all. From there you pass Jupiter and Saturn, the solar system's two largest and heaviest planets, gas giants with no solid surface to speak of, followed by the ice giants Uranus and Neptune, worlds so distant that sunlight itself takes hours rather than minutes to reach them, and finally out to Pluto, a world that was once counted among the solar system's major planets, and now is not even officially considered one, having been reclassified as a dwarf planet by the International Astronomical Union back in 2006. By this point, you are more than 4 billion miles from home, a distance that took NASA's New Horizons probe about 9 years of real flight time to cover before it finally performed history's first close flyby of Pluto in July of 2015, revealing a world with towering water ice mountains and vast plains of frozen nitrogen that nobody had expected to find on such a small, cold, distant body. Keep going and you cross the Kuiper Belt, a vast ring of ancient ice and rock left over from the solar system's formation, and believed to be the source of many short-period comets, before finally reaching the true outer boundary of the sun's influence, the heliosphere, where the solar wind that has been carrying you outward finally collides with the thin gas of interstellar space and slows down dramatically at a boundary called the termination shock. Only one human-made spacecraft has ever actually made that entire journey for real. Voyager 1 reached the termination shock in December of 2004, and it would take nearly 8 more years of travel before it crossed the true edge of the solar system, the heliopause, in August of 2012, becoming the first human-made object in history to enter true interstellar space. Confirmation of that milestone did not reach Earth for more than a year after it happened, since even radio signals traveling at the speed of light take significant time to cross such enormous distances. It took Voyager 35 years to get that far, and the probe itself is roughly the size of a small car, carrying a golden record engraved with images of Earth, recordings of human languages, and diagrams of our DNA, a message built for any civilization that might one day intercept it. As of the most recent tracking data, Voyager 1 has been operational for well over 4 decades, has traveled more than 14 billion miles, the equivalent of over 150 trips between the Earth and the Sun, and continues drifting outward at roughly 38,000 miles an hour, carrying humanity's furthest flung physical object ever further from home. Push our faster-than-light spacecraft onward, and you next reach Proxima Centauri, the nearest star to our own sun, so distant that even light itself needs more than 4 years to make the crossing, a trip that would take a conventional rocket around 73,000 years. Proxima Centauri hosts an Earth-sized world called Proxima Centauri b, roughly 10% larger than our own planet, and sitting inside its star's habitable zone, the region where liquid water could theoretically exist on the surface. Unfortunately, Proxima Centauri is a volatile red dwarf prone to violent flares, and during one especially intense outburst, its brightness spiked by nearly 1,000-fold, an event that would have blasted enough radiation across the planet to sterilize any surface life that happened to be there at the time. Continue on and you eventually reach Sirius, the brightest star in Earth's night sky. So brilliant it is sometimes visible even in daylight, and in reality not one star but 2 locked in a mutual orbit, drifting toward our own solar system at nearly 5 miles per second, roughly the top speed of a high-performance supercar. Farther still, some 39 light-years from Earth, sits TRAPPIST-1, a small, cool, red dwarf star, roughly 10 times smaller and lighter than our own sun, orbited by 7 roughly Earth-sized planets discovered in a single remarkable announcement in 2017, one of which, TRAPPIST-1d, is considered among the most Earth-like worlds ever discovered, only slightly smaller and lighter than our own planet, with an estimated surface temperature mild enough that a light jacket might genuinely be all you would need. Assuming it has the atmosphere and liquid water scientists suspect it might. Reaching it with conventional rocket technology would take an estimated 677,000 years. And then, finally, after traveling far enough that entire star systems have blurred past like scenery, you arrive at Betelgeuse itself, a star so enormous that, even traveling many times the speed of light, the trip from Earth using anything close to current technology would take somewhere in the neighborhood of 8.5 million years. Up close, Betelgeuse is so large that your spacecraft would look like a single grain of sand on an endless beach. To understand how it got this way, and where it is headed next, you have to go back to the beginning of its life. Betelgeuse was born inside a nebula, a sprawling cloud of gas and dust that slowly collapsed under its own gravity until the pressure and heat at its core ignited nuclear fusion, and a star was born. In its youth, Betelgeuse was extremely hot and massive, but comparatively compact and stable, held in a careful balance between two competing forces. The outward pressure, generated by nuclear fusion in its core, pushing against the inward pull of its own gravity. For most of a star's life, those two forces roughly cancel out. But once a star like Betelgeuse burns through its central supply of hydrogen, it begins fusing progressively heavier elements, and the outer layers of the star swell outward dramatically even as the core itself continues to contract, transforming what was once a comparatively ordinary massive star into the sprawling red supergiant we see today. That expansion is also the source of Betelgeuse's famous restless flickering. According to the same 2020 modeling study that recalculated the star's mass and distance, Betelgeuse is a pulsating variable, driven by what astronomers call the kappa mechanism, in which fluctuations in the opacity of the star's outer layers cause it to rhythmically brighten and dim on two overlapping cycles, one lasting roughly 185 days and a longer one lasting around 400 days. That same research placed Betelgeuse firmly in the early stage of core helium burning, the phase that follows hydrogen exhaustion, which turned out to be enormously reassuring news because it meant the star likely has on the order of 100,000 years left before it actually explodes. An eye blink on a cosmic timescale, but a comfortably long stretch of ordinary human history by any earthly measure. Even more surprising, a 2024 study analyzing Betelgeuse's long-term radial velocity variations proposed that the star might not actually be alone at all. Researchers found evidence consistent with a small, low-mass companion star locked in a wide orbit around Betelgeuse, one that could help explain a longer, roughly 6-year brightness cycle astronomers had puzzled over for decades, separate from the shorter pulsation periods driven by the kappa mechanism. If confirmed, this hidden companion would likely be swallowed whole by Betelgeuse's bloated outer atmosphere within the next few centuries, spiraling inward and eventually being consumed entirely before the supergiant itself ever gets the chance to explode. A strange and almost tragic footnote to an already dramatic stellar story. Which brings us back to the Great Dimming of late 2019 and early 2020, and what astronomers eventually discovered was really happening. Using observations from the Hubble Space Telescope, a team led by astronomer Andrea Dupré found clear evidence that Betelgeuse had recently ejected an enormous amount of hot plasma from its southern hemisphere, material equivalent in mass to several moons. As that ejected material drifted outward and cooled, it condensed into a vast cloud of dust directly in our line of sight, essentially casting a shadow across a portion of the star's surface as seen from Earth. It was not the star, growing dimmer from within, and it was absolutely not the beginning stages of a supernova. It was an enormous cosmic dust cloud temporarily blocking our view, the stellar equivalent of a curtain briefly drawn across a stage. By the middle of 2020, Betelgeuse had already brightened again, and follow-up studies using both ground-based telescopes and additional space-based observations confirmed the same conclusion. The star's core was continuing to quietly burn helium exactly as expected, with no sign of an imminent explosion at all. Reassuring as that is, Betelgeuse's ultimate fate has never been in question, only its timing. Eventually, once the star's core exhausts helium and begins fusing progressively heavier elements, carbon, then neon, then oxygen, then silicon, each stage burning faster and lasting a dramatically shorter time than the one before it, the core will finally begin forging iron. The speed of that final countdown is almost impossible to grasp. While hydrogen burning can sustain a massive star for millions of years and helium burning for several 100,000 more, carbon burning is expected to last only a few hundred years, neon burning a matter of months, oxygen burning mere weeks, and silicon burning the very last stage before collapse burns itself out in less than a single day. Iron is where the process stops being able to release energy through fusion at all, since fusing iron actually consumes energy rather than producing it. And at that point, the delicate balance that has held the star together for millions of years collapses in an instant, quite literally, the iron core imploding in a fraction of a second under its own crushing weight. That implosion triggers a catastrophic rebound that blows the star's outer layers off into space in what astronomers call a core collapse supernova, releasing more energy in a matter of seconds than the sun will produce over its entire 10 billion year lifespan. Because Betelgeuse still retains a substantial hydrogen envelope, astronomers expect its eventual explosion to be what's known as a Type 2P supernova, a category defined by hydrogen lines in its light spectrum, and a distinctive plateau in its brightness curve as the expanding shell of hydrogen gas briefly stalls its own fade, keeping the supernova shining at roughly the same brightness for weeks or months before it finally begins to dim in earnest. Given its mass, somewhere in the range most strongly associated with leaving behind a dense, city-sized stellar remnant called a neutron star, rather than collapsing all the way into a black hole, which typically requires an even more massive progenitor. Either way, the explosion itself would be almost impossible to overstate. For weeks, potentially even months, Betelgeuse would likely become bright enough to rival the full moon in the night sky, visible even during broad daylight, an event unlike anything most of the roughly 8 billion people alive today have ever witnessed. The best real-world precedent for what such an event might actually look like from Earth comes from a supernova that was not even in our own galaxy. In February of 1987, astronomers detected a supernova in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way roughly 168,000 light-years away, an event now catalogued as SN 1987A. In the hours before the explosion became visible to optical telescopes, underground neutrino detectors on the other side of the planet registered a sudden, unmistakable burst of neutrinos, ghostly, nearly massless particles produced in enormous quantities during a core collapse, which travel at nearly the speed of light and pass through an exploding star's outer layers almost instantly, arriving hours before the visible light finally fights its way out through the star's dense envelope. That handful of neutrino detections, only about 24 particles caught across multiple detectors worldwide, remains the only confirmed direct observation of neutrinos from a supernova in history, and it gave astronomers a genuine practical head start warning system. If Betelgeuse ever does go supernova, the same physics applies. A burst of neutrinos would wash over Earth's detectors hours before the visible explosion finally became apparent in the night sky, giving astronomers around the world a real, if brief, advance notice to turn every available telescope in Orion's direction before the light show even began. Despite how dramatic that would be, there is essentially no danger to life on Earth. Astronomers generally consider a supernova dangerous to a nearby planet only within a range of roughly 25 to 50 light-years, close enough for the burst of gamma radiation and high-energy particles to meaningfully damage a planet's atmosphere and ozone layer. At 548 light-years away, Betelgeuse sits more than 10 times beyond even the outer edge of that danger zone, comfortably distant enough that Earth would experience nothing more than a dazzling light show and, potentially, a brief, barely measurable uptick in cosmic ray activity. No known star close enough to Earth to pose any genuine existential threat is currently expected to go supernova anytime remotely soon, which makes Betelgeuse something rarer and more valuable than a danger, a nearby, safe front-row seat to one of the most violent and instructive events in all of astrophysics. The most recent supernova visible to the naked eye from Earth, a star now catalogued as SN 1604, or Kepler's supernova, appeared in the year 1604 and was observed and documented by astronomers across Europe and Asia, including Johannes Kepler himself, whose detailed notes on the event still inform supernova research centuries later. Before that, Tycho Brahe recorded a similarly bright stellar explosion in 1572, an event so unexpected that it helped overturn the prevailing ancient belief that the heavens beyond the moon were permanent and unchanging. Centuries earlier still, in the year 1054, Chinese and Arab astronomers documented a supernova so bright it remained visible in daylight for weeks, leaving behind the twisted, glowing remnant we now know as the Crab Nebula, still expanding and still being studied by telescopes nearly 1,000 years later. No supernova bright enough to see without a telescope has occurred anywhere in our galaxy since Kepler's star more than 4 centuries ago, which is part of why Betelgeuse's eventual explosion has captured so much public fascination. It would be the first naked-eye galactic supernova witnessed since telescopes themselves were still a brand new invention, and the first one ever observed by a civilization equipped with neutrino detectors, space telescopes, and the ability to watch the entire event unfold across every wavelength of light simultaneously. There is one genuinely strange wrinkle in all of this that is worth sitting with for a moment. Because light from Betelgeuse takes roughly 548 years to reach Earth, everything astronomers currently see when they look at the star is already more than 5 centuries old. A snapshot frozen in time from around the year the Mayflower's grandparents' generation was still walking around. It is entirely possible, purely as a matter of light travel time, that Betelgeuse has already gone supernova sometime in the past several hundred years, and that the news simply has not finished making its way across the galaxy to reach us yet. If that turns out to be the case, the explosion could already be underway, or even complete, and humanity would have no way of knowing until the light physically arrives at Earth. Whether that happens tonight, next year, or in another 99,000 years, well within the window astronomers currently consider most likely. It is a strange thought experiment, staring up at a star that might, in some very real sense, no longer even exist in its current form, and having absolutely no way to check. For now, Betelgeuse continues doing what it has done for as long as human beings have watched the winter sky, marking the shoulder of Orion with its distinctive reddish glow, quietly burning helium in its core, occasionally shedding vast plumes of dust and gas that make it flicker and dim in ways that still occasionally startle astronomers into wondering if this is finally the moment. The 2019 to 2020 Great Dimming turned out to be a false alarm, but a genuinely useful one, giving scientists an unprecedented real-time look at exactly how a red supergiant loses mass in the final stretch of its life. Data that will help astronomers recognize the real thing far more quickly whenever it eventually happens. Telescopes and neutrino observatories around the world continue to keep half an eye on Orion's shoulder every single night, not because anyone expects the explosion tomorrow, but because after the events of 2019, nobody wants to be caught off guard again if the star does something unusual a second time. Some astronomers have only half-jokingly suggested that professional and amateur observers alike should treat any future dimming event with the same mixture of excitement and caution, ready to point every available instrument skyward the moment the neutrino detectors buried deep underground register even the faintest unexpected flicker. Somewhere out there, whether already collapsing in the past or still patiently burning helium exactly as current models predict, Betelgeuse is counting down toward an explosion that will briefly become one of the brightest objects in Earth's entire sky. A supernova so far away it poses no threat to us whatsoever, and so close in cosmic terms that it might just be the most spectacular astronomical event any living human being will ever witness. Whether that moment arrives tonight, sometime within the next century, or not for another 99,000 years, the star currently marking Orion's shoulder is already, quietly and invisibly, running out the clock on one of the most dramatic endings the universe has to offer. And all of us, whether we ever look up and notice it or not, are simply waiting for the light to finally arrive.